Hello and welcome to another episode of TWIML Talk, the podcast where I interview interesting people doing interesting things in machine learning and artificial intelligence. I'm your host, Sam Charrington. While at last year's NeurIPS conference in December, I attended the second annual Black in AI workshop, which gathered participants from all over the world to showcase their research, share experiences, and support one another. Today, we conclude our Black in AI series with this interview with Sicelukwanda Zwane, a master's student at the University of Witwatersrand and graduate research assistant at South Africa's Council for Scientific and Industrial Research, or CSIR. At the workshop, Sicelukwanda presented on safer exploration and deep reinforcement learning using action priors, which explores transferring action priors between robotic tasks to reduce the exploration space, which in turn reduces sample complexity. In our conversation, we discuss what exactly safer exploration means in this sense, the difference between this work and other techniques like imitation learning, and how this fits in with the broader goal of lifelong learning. Enjoy. All right, everyone. I am on the line with Sicelukwanda Zwane. He's a master's student at the University of Witwatersrand and a graduate research assistant at the Council for Scientific and Industrial Research, or CSIR, in South Africa. Sicelukwanda, welcome to This Week in Machine Learning and AI.
Thanks a lot, Sam. Thank you for having me.
So I will just let everyone know that you were very, very gracious in practicing the pronunciation of your name with me, and I am still butchering it, but thank you so much. We had a long practice session before, and I am going to work on these Xhosa clicks?
It's Zulu. It's actually
it's Zulu. Sorry.
Yes, but it tends to be very similar to Xhosa.
Okay, so I'm going to work on this, and the next time we have you on the show, we're going to get it. But thanks so much for your patience with that. Why don't we get started by having you share a little bit about your background and how you got started working in machine learning and artificial intelligence?
So I got into machine learning because of the problems that I found back when I was in this interest group in second year, where we were this robotics interest group at WITS, and we were given these quadcopters to fly around, and my friend and I decided we want to fly ours in like a rectangular shape, and we found that we couldn't do that. We had issues with things like wind and momentum. You could never actually get the drone to be in one particular position. But nonetheless, even though we did fly in some type of kite shape, I found myself fascinated by the fact that I basically wrote some code and I had to sit back and relax and watch my code basically fly this machine around, right? So actually, I became interested in the field of robotics and continued my studies and tried to pick subjects even in honors that would basically give me a good start in my career as a roboticist in South Africa. Then I think during my honors year, one of the subjects that I picked was reinforcement learning, and there I learned that the big thing, or rather the big challenge in trying to get machines that can think and act like human beings is not so much the actual machinery and trying to create something that is anatomically similar to a human being, but the bigger challenge was trying to get these machines to perform like these complex behaviors, like things like that we take so much for granted. Something as simple as picking a pen up or picking a cup up and putting it down is something that is still a difficult task when you want to achieve it with a robot. Or rather, the bigger challenge was this thing, generalization. We want to have we want these machines to be able to perform general behaviors. If I say pick something up, you shouldn't care what the object looks like. You shouldn't. Your code shouldn't rely on the actual position of the hand when it does it. It needs to generalize to all these like weird scenarios. For example, if someone has a bigger cup, if someone has a mug, if someone has a pen, and it turns out that machine learning, or I found out that machine learning was one of the tools that could actually help achieve this goal. Through machine learning, we can actually learn more general behaviors, to get more interesting robotic applications, or more useful. Actually, useful is the word I was looking for there. So yeah, like that is literally how I got into the field, just by wanting to see a robot perform some simple task, and then realizing that having the robot perform that task is not something that is simple to say. It wasn't trivial, like one alternative, or as a third-year computer science student, I think my skill set would have probably pointed me towards trying to hard code. Okay, maybe tilt the robot hand by 45 degrees and then move it forward a few centimeters and then go down and then open the gripper, close the gripper and then pick it up. But you realize that you just you created this behavior is only specific to this particular scenario. Like you leave your robot overnight at the lab and someone comes and they move the cup by a few centimeters and now your whole system doesn't work. So the reason why I'm interested in machine learning, or the reason why I'm in machine learning, is to be able to learn more general behaviors, more useful behaviors for robots and other applications. Because machine learning is not only useful for robotics, just that is my interest there.
One of the things that I can really relate to is that initial inspiration. I find I really enjoy, I don't code a lot, but I do enjoy it. But when you're writing code and then that is affecting the physical world through motors and other actuators, basically robotics, whether in like small form, making lights blink, all that kind of stuff, I find it super rewarding. And so I can see how that would get you kind of pulled into wanting to explore more and have more, kind of be able to build these more robust interactions.
Yeah, no, that's precisely the point, right? There's so much. It is actually very rewarding to see something that you created actually become something physical that you can see.
At the Black in AI workshop, you presented on some of your research titled Safer Exploration in Deep Reinforcement Learning Using Action Priors. Tell us a little bit about the motivation for this project.
Okay, the motivation is not really a straightforward thing for me. What motivated me to go with this particular topic is mainly my experience with using deep reinforcement learning and trying to apply it to the robotics domain, right? So I have access to this mobile manipulator. It's basically just a PowerBot AGV platform with a Barrett WAM 7-DOF robot arm on top, and we would like to. Basically, the dream is to have this platform performing complicated tasks such as making someone coffee or making a sandwich and things like that. But it's really hard to specify rewards and it's very hard to produce those kind of behaviors if you are trying to manually specify what is supposed to happen. Like ideally, we would like the system to actually learn to perform these behaviors on its own.
So what I'm kind of hearing here is you kind of started out, as an undergrad, trying to get robots to do things. And, at that stage in your experience, kind of the natural way to do things was to build these big, rule sets, if then else kind of programming. And you went on to explore doing this with deep reinforcement learning, but then you ran into this challenge of how do we create the reward functions to get a robot to grip something? That's historically one of the hard parts about using deep reinforcement learning.
Yes, that is correct. So I found it very hard to specify a reward function for picking something up. My first task as a master's student was, okay, I want to use deep reinforcement learning to perform multitask learning on this particular robot platform that we have at the CSIR, right? Then when I'm thinking about doing that, I realize, okay, this is basically one of the few robots that we have, and reinforcement learning is known to be random in nature, right? You rely on maybe executing random actions to kind of discover rewarding states and stuff like that. And you can't really afford to be performing these random actions and these jerky movements when you're actually working with actual machinery or the physical platform. So my first task was, let me just build a simulated environment. And as I was doing that, I spent some time trying to basically find the right meshes that would kind of correspond in shape and size to the actual physical platform. And I was using this thing called Gazebo, where you can basically have like a physical environment, with all the physics and collisions and things. And
right.
then
Gazebo is like a physics simulator that's used quite a bit in robotics. Is that right?
Yes. So yeah, when I say built, is that I built basically some packages for this particular platform that would allow me to use reinforcement learning with the actual joint configurations of the robot. So things like I need to be able to publish actions to the robot and have it perform those actions and then observe some change and then have something that's going to decide if this was good or bad, which is basically my reward function, right? So yeah, but the whole thing was just I want to have this particular robot platform being able to perform multiple tasks. And on my way there towards performing multiple tasks, I realized that, okay, there's actually a lot of challenges with getting a standard deep reinforcement learning algorithm to work properly on like any environment that you have, right? So when I think about a deep reinforcement learning, I'm going to be thinking about, okay, firstly, you have this exploration phase where you start with random policies, right? And you're going to be trying to find, I guess you'll be executing random actions. I found out that it was really hard to specify reward functions for these complicated behaviors. Like, for example, in wanting to pick something up, right? You need to somehow reward the agent for what's this thing reaching towards the object and then actually picking it up, which is, there's actually two stages. You need something that's going to encode moving towards the object and something that's going to encode basically you closing your gripper around the object and then still having the object and moving your hand up and having the object remain in the hand, so things like that.
You presented a project called Safer Exploration and Deep Reinforcement Learning using action priors. First off, when you say safer exploration, what does that mean and why is that important?
Yeah, so when I'm talking about safer exploration, right, I'm trying to improve the safety of the exploration policy in a standard deep reinforcement learning algorithm, right? So being in the robotics domain, I care very much about the physical well-being of my platform, right? So it's very important to me that I won't be, if, for example, I need to learn to perform some task using the deep reinforcement learning algorithm, I need some form of insurance that my platform won't be basically performing the worst possible thing. It won't hurt itself in any way. For example, if I have like a Roomba and basically having it sweep my roof for some odd reason, right? I need to know that this thing won't drive off the roof, like things like that. Like it should be able to learn, right, in this scenario or in an environment where there are still states that are deemed very unsafe or like very undesirable, right? So when I talk about safer exploration, I'm just trying to, I guess, improve the safety of your standard deep reinforcement learning algorithm. I mean, that paradigm is based on, so you understand the standard paradigm in reinforcement learning in general is that or one of the more popular exploration techniques is this epsilon greedy thing where you're going to decide, okay, I'm going to execute some random actions or actions from a random policy, right? Some epsilon probability of the time, and then with probability 1 minus epsilon, you're going to be basically exploiting or you're going to be executing actions that come from the policy that you're training, right? Which is also quite random initially. But you do this so that like you can actually discover like potentially useful actions to perform in any state, in the state that you're currently occupying. So my work is to trying to kind of relax this very random nature, right? When you're exploring. And what I'm saying is that instead of trying to explore randomly, right, or executing random actions, why don't we execute actions that were performed by experts in these like states that we're in, So you'd have maybe something like you try to first build some notion of account, right? To maintain, you'd maintain some notion of account to see how many times a particular action has been performed in a state, right? And then you're going to explore according to these counts. So you convert these counts to a probability distribution, and then you sample from this distribution, and that is the action that you're going to apply, right? Like a more intuitive example is something like if I gave you the task of opening a door, right? The first thing, if you're a reinforcement learning agent and you've never opened a door in your life, the first thing you do when you're in front of the door is that you're going to try every possible action, right? And you're going to try very random things. So now in your action space, you have the action of licking the door handle, which is, could not lead to you opening the door. You can try kicking the door. There's so many things you can try. But if you have the opportunity maybe to sit on a chair next to the door and watch how other people do it and then try what they're trying to do, like these people may be trying to do other things with the door, but the hope is that by trying what other expert agents have tried in this particular state, you may be you may avoid this random nature like that may lead you to undesirable states. Like it kind of grounds your search for good actions, and also because these agents that you're watching are expert agents, you can assume that they are behaving optimally or in a way that they are not trying to harm themselves in any way.
So when I hear you describe it like that, the thing that comes to mind for me is imitation learning. How is that related to what you've done here?
So how I understand imitation learning is that you're going to be observing, I think you're going to have access to some expert trajectories. And I think the task today is to try and follow those, right? You're basically trying to make those trajectories more general in a way. You want to kind of imitate the expert, right? Whereas here, what we're trying to do is that we're not really performing the same task as the expert that we're watching, right? So the action priors framework has the flexibility that the different experts can be performing different tasks, right? And by different tasks, I mean tasks that have different reward functions, right? Meaning that it doesn't matter what the action that the experts are doing, as long as the action spaces are the same between the agent that is learning and these experts here, right? You may find some benefit in basically trying what the experts, tried. Like if that makes sense, you're trying to act according to this body of advice. Like I think advice kind of makes more sense, right?
So if I can recap what you're saying to make sure I understand, when in imitation learning, if you've got our scenario with the robot sitting in a chair observing an expert interacting with the door, in imitation learning as it's classically defined, what you're really trying to do is have the robot, look at someone performing a very specific task like rotating the door handle thousands of times or however many times, and you're trying to teach it that very specific action. And any other actions would be noise in that kind of model. Whereas in what you're doing, you're presenting just kind of not random observations, but observations of a bunch of different things, reaching for the door, turning the knob, opening the door. It's more unconstrained, and you're trying to use all of these observations to kind of condition the exploration process.
Yes. That's exactly what I'm trying to do.
Okay.
So yeah, it's just as you put it, an unconstrained, I guess, version where you have all these multiple demonstrations. You're not exactly trying to follow any particular trajectory, but what you're interested in is what these experts are kind of doing in any particular state. So if you visit a state, you can always ask the question, what did experts do, right? And maybe there will be some arbiter or some oracle that will tell you, hey, 63% of experts took this action, maybe 23% of experts took this action, and then other experts took this particular action, and no expert took this particular action, right? So then I want to, in that case, basically try the actions that were more popular as opposed to the one that the experts didn't try, because you can imagine that in a model like that, you're kind of implicitly representing, in this case, I guess, the state space in the environment, and maybe the experts in this particular state are not moving forward, are not taking the action for going forward because this is a cliff, right? So as they were training, they found that, okay, when they went forward, this led to a very bad reward. So they decided, okay, I'm not going to take that action. I'm just going to do this and that. So it's basically you treat it as this body of advice that you can kind of query at every step in your exploration process.
One question I'm curious about is how you define the state space, and if you're doing anything to generalize it. And I realize there's a lot of loaded language there. What I mean is kind of going back to this example of the robot observing the expert. If the expert is reaching for the door handle, you could learn a lot about that action. But if you're only able to access what that expert has done, if the robot is in the exact, if all of the dimensions of the robot, it's all of its positions are in the exact same point, then you kind of miss out on a lot of advice from experts who were their hand was doing the same thing, but it was shifted over a centimeter or something like that.
Yeah. That's the question of portability, right? So this in the original paper, right? The way the authors basically tackle this problem, right, is by introducing a second version of the action priors framework, which was conditioned on observations instead of the state, right? So obviously, if you're trying to learn this distribution over actions given a state, right, basically asking, okay, what action should I take at this particular state? You are only going to, that model is only going to be useful should, like in an environment where the state space doesn't change. So essentially, if there's an obstacle here, that obstacle should not move at all, right? And the walls would stay the same place and stuff like that. But as soon as you move like an obstacle or something that was not, like for example, if you were training in an environment where, let's say, the obstacle is in one particular position, right? And then now you take demonstrations from that setting and you try to move it into a setting where the agent is training, where these obstacles have been moved around now. What's going to happen is that information is not going to be portable, right? So to try and fix that problem, or to fix the problem, what the authors did, this is Benjamin Rossman and Subramanian Ramamurthy, I think, if I remember correctly. What they did is that they conditioned the action prior distribution over observations, meaning that I guess if you can imagine if all the obstacles were blue and your agent can be like, or your body of advice could be something that says, okay, if I see a blue thing, I want to do this or this, So basically, whenever I see an obstacle, I want to do one of the following deterministic things, So you can increase the portability of this action prior framework by just conditioning on observations instead of the state.
I guess I'm trying to visualize how you represent the state for a given problem. How do you figure out, is the representation like I'm imagining it's a vector of some sort, but is it a vector of like if it's a robot, like all of the stepper motor angles and that kind of thing, or is it something else? Is it more abstract?
No, it's exactly it's exactly that. So if you have a robot, like a robot arm, then it will be your joint angles and stuff like that. It's literally So how I think of reinforcement learning in general is that you're going to have some target environment, and then you can have a state, right? Defined in the framework of a Markov decision process. You can have a state, and then you have access to actions, and there's a transition function, and then you have a reward function, I guess, in some gamma discount factor thing. But yeah, like a state can mean anything that you want it to mean, as long as you have formulated the problem you're trying to solve as a reinforcement learning problem. Like that's how I think about it. So in my case,
so then the question that I was trying to get at in this case is, let's say that your state vector is all of your angles, and you've got this. You're basically able to consult the oracle, so to speak, to see if it knows anything about what to do in a given state. I guess the question that I'm asking is, like, when you consult the oracle and you say, like, these are my, angles out to the second decimal point, the second decimal place, will it return what it knows, even if it's not exactly that, but kind of close? Or do you have to kind of generalize it or round it before you consult the oracle? Or will you only know about things that happen at the very exact places? Does that make sense?
Yeah, it does. So that's a very good question, right? So that is precisely the challenge with trying to move. Okay, let me just first say this action priors framework was defined, I think, for it to work very well in the discrete setting, which is true for most deep reinforcement learning and reinforcement learning algorithms, right? And moving into a continuous setting where you don't really have any guarantee that you'll ever see the same state again, there is a need for models that can generalize, like in some region and say, okay, for this particular region of state space, this is what the action distribution looks like, and stuff like that. And I think that is what motivated my choice in what model to use to represent the action prior. So in this case, that was a Gaussian process, which has a very nice smoothing effect, like as far as data is concerned.
Okay. Yeah. Now that you've said it, all of the language that I should have been using to ask the question is obvious, like discrete versus continuous, and so just maybe to take a step back to make sure I understand. The question I'm curious about now is how your specific research fits into the broader landscape of research in this area.
Okay, so how I thought about it, right, was basically, if you want to have a robot that can perform multiple tasks and things like that, right? If you want a robot that is going to be useful in any particular scenario, then you need to think about, I think the field is called lifelong learning, right? And lifelong learning is basically trying to get these systems that can basically learn tasks as they are presented, either in parallel or sequentially, and then retain their ability to perform those tasks, and then somehow use the knowledge that they have gained in learning the previous tasks to improve the learning of concurrent tasks. And I think that's almost how humans do this learning thing, right? So if I then think about the challenges that you get there, the first one is just trying to perform successful transfer learning and in my case in continuous settings. So I can imagine that the action priors framework kind of fits somewhere in between in between having like a full or rather it's one component that you would need to have a lifelong learning system or a lifelong learning robot. Okay. So for example, my whole pipeline would be something like you train some expert agents in some target environment, right? And then these expert agents or these tasks, right, that you're trying to learn can be, all basically learned by the same robot, so to speak. And then this particular robot would use or sample trajectories or like keep a data set of trajectories from these learned tasks, right? And it would fit this model, this action prior distribution over those trajectories. And then for every task that it wants to learn, it can basically explore according to this action prior distribution. And after it has learned this new policy, it can then sample trajectories from there, augmenting its data set, and then, fitting the distribution again, and then when learning a new task, it then going to use the exploration policy again. And then that just keeps going on until you have this machine or the system that can perform, multiple tasks and things like that. So I like to think of it as, I guess, a step towards lifelong learning. And one of the problems we have there in lifelong learning is we need to, I guess, solve the problem of transfer, as well as, if you're talking about deep reinforcement learning, you need to kind of worry or at least dedicate some time towards how to do exploration more efficiently and more safely.
Before this explanation, when we were talking about experts, I was thinking in terms of observations. So your system would have some set of observations, and those represent the experts. But you just introduced this concept of training expert models. How is that done? And kind of how is that different from the ultimate model that you're trying to train with reinforcement learning?
So you please repeat the question. So it's are you asking if how different is having this whole notion of an expert model compared to having what?
Reinforcement learning. Like the expert model is presumably the expert model is simpler and more readily trainable than a DRL model. Is that true, or are the experts also trained using reinforcement learning?
So in this case, I think my notion of expert, or how I think of expert, of what an expert is, it could be a deep reinforcement learning agent that was learning a task in the same environment, and now I just sample trajectories from the policy that I get from there, and then I use those samples to train the agent that I'm going to train next on a different task. It could also, expert can also mean, just some, I guess in the context of video games, you can find that maybe a human player can kind of demonstrate what the correct actions or the correct policy is by playing the game and giving the reinforcement learning agent this trajectory that goes through the game in some sort of optimal way. And so it's basically either your expert is either agents that you were training in the same environment, or it could be just some human demonstrations and things like that. So in the context of I think learning from demonstration, when you're talking about robot manipulators, you can have someone who's trying to teach a robot how to wave by actually performing the action themselves and then recording that trajectory. So I think the notion of expert in this case is just a bit more general.
Say we're back at the door, and is the idea that we would have separate expert models for reaching and turning and pulling and that kind of thing, or is there one expert that knows how to open a door?
So I want to say maybe in training an expert how to open a door, right? You'd use information from these other experts, right? So reaching a door and turning the handle could all be actually useful actions.
Okay.
But in that case, this task is it feels like it's arranged in a sort of like a hierarchical way, where turning the door could be considered as some kind of opening the door could be considered as some kind of macro action that is composed of these smaller policies, such as reaching for the door handle, turning the handle, and then pulling.
Right.
So and the action priors framework, I'd like to think, is more primitive in the sense that it's not hierarchical in any sense. It doesn't really, although you can kind of make it hierarchical by using options and other stuff like that. But my particular use case is using action priors or rather the action priors rely on actions that are kind of primitive, So as long as my experts have the same action space and state space, then I can be able to use trajectories from other expert models or trained models and use them to train one particular target task faster and safer.
So in other words, if you're trying to train an agent to open the door, you don't really care. You may have access to these experts that were trained on these subtasks, but you don't really care about that implicit hierarchy. You're just you're asking the question, hey, the arm is here. What do experts usually do when the arm is here? And then sample from a distribution of that answers that question and use that to inform your next step.
I'm trying to move, or rather trying to think independent of, or rather I'd like my model to kind of not consider the reward functions or like what tasks was being performed by any particular expert. Right.
Okay.
Because it makes sense for me to use data from an expert that was performing a very similar task. And now when I say similar task, I have to, in my pipeline somewhere, consider how am I going to compare task similarity? Like how do I know that this robot is performing a task that is similar to this one before deciding to sample trajectories from the policy that I got from this one, right? So it's something like if I have this library of policies that do multiple things, the first task is to first maybe traverse through all these trained policies, checking to see how similar these tasks that they're performing to my tasks, to the task that I'm interested in. And then after finding the one that is most similar, then I can now perform transfer. But I guess what I'm trying to do here is trying to perform multitask transfer, which is basically you just have this library of tasks, and you're trying to extract some common knowledge from them, and then use whatever body of common knowledge to kind of speed up or improve the learning of some task that you're interested in.
You're not looking at task similarity at all. You're just looking at, what do we know about what these experts do when we're in this state?
Yes. So I'd like to think of transfer as like falling into two categories, right? And the first one would be aggregate transfer, right? Where I'm trying to transfer from all the tasks that I have. And then the other version of transfer would be kind of more selective to say, okay, in this library of tasks that I've learned, these maybe 3 tasks are very similar to the tasks that I'm trying to learn. And I'm going to take these 3 and transfer only from those, right? So, yeah, and then when transferring, we also need to be careful of things like negative transfer, because you can imagine that not all that knowledge is going to be useful. Some is actually going to be very bad for, it's going to hurt the learning of this target task if you're not careful. And you can imagine that's one challenge that I kind of have to worry about here.
Mm-hmm. So again, taking a step back to understanding the specific focus and contribution of your research relative to the broader landscape, it sounds like action priors is already out there. Epsilon greedy exploration policy we know is already out there. Is what you're adding here the idea of this multitask transfer from multiple action priors, or is it something else?
Oh, it's essentially the extension of the framework to continuous settings,
Okay.
So
right,
for example,
right.
Yeah. So just trying to understand how you can still maintain a notion of account in a continuous setting, because if you think about having a discrete space, like for example a maze with tiles as states, it's easy to basically keep some table where you're like, okay, this particular action has been performed this many times, and this action has been performed this many times, and then you build a distribution over that. You sample over from that categorical distribution, and you get an action out, right? But now, how do you do that for the case where you don't really have the ability to even kind of maintain account, because you essentially have, as soon as things become continuous, you kind of have infinitely many states, right? And the other thing is that you get this effect of multimodality, where at the same state, you need a model that can kind of represent these different action preferences, like or these action preferences from this data like that you have, these trajectories from the experts that you have. Like for example, if we're talking about maybe, let me see, so you have an action space where actions can range from -1 to 1, right? And you can imagine that maybe in this particular setting, most experts prefer an action of 0.2 or around. They prefer an action that has a mean of 0.2, and other experts can have a preference around maybe of -0.7 and things like that. But then there's places where if you were to put a mean around there, like that would result in a very, very bad kind of policy, So it's kind of like you have a one-to-many mapping, right? At every point in the state space, right? And that is not really, in my experience, it hasn't been very trivial to kind of learn, because I think neural networks are kind of, they're more for kind of one-to-one type of mappings, where you have like input they're more for many-to-one type of scenarios where you can have multiple inputs, and then you have like one kind of output in the end. But what happens when you have like a single input, which is like your state, and then you have all these like possible Y values that you have to get out, So my experience with using just like a standard neural network is that you get this averaging effect, and I've noticed that the average of expert actions in a particular state is not an expert action, or is not an optimal action. Yeah. So in the scenario of, I guess, a self-driving car, you can imagine that you're driving into like a kind of fork, right? And then in the middle of the fork, there's something like a tree or something like that. And then your experts would be going either, have a steering angle of like -0.5 at the decision point, and then other experts have like, I guess, 0.5. And then what happens in that case is that if you try to learn your action prior distribution or action preference distribution at the decision point, you might just average over the two, and you get like a steering angle of 0, and that says drive straight into the tree, and then that's not useful at all. Especially if you care about your cause. Yeah.
And so how does this model compensate for that?
The framework does compensate for that, but I have been looking at models that try to look at how to represent a multimodal policy. Like, for example, especially since I'm talking about probability distributions, or it's kind of like I'm working with Gaussian mixture models, right? So I need something that will basically take in a state and then give me a mixture, a Gaussian mixture model of sorts over the action space. And recently, I've been playing with things like mixture density networks, and those have been giving me promising results. And then there's still like some ammo of models that I have. I guess I heard about. I think it's overlapping mixtures of Gaussian processes, and basically it's just models that have support for. Or models that can give you multiple outputs given a single input, So yeah, that's kind of the challenge here.
So is the idea that, kind of referring back to your self-driving car example, that given your state, one of these mixture models would be able to tell you that there are two distributions that are likely, one is centered at -0.5 and the other is centered at 0.5. And then based on that information, you would know to choose one of those as opposed to choosing the 0 or averaging out to 0.
Yes. That's exactly what I'm trying to do. And actually, you highlighted another problem there, right? Which is, how do you choose how many modes there are? No one is going to tell you that the good kind of behaviors here, there's only two of them, meaning that you have like two kernels or two modes, like in your mixture model, right? Meaning you got your go left and then go right. That kind of thing can change at different points in the state space. Maybe some states have got like an action preference distribution where like experts are doing kind of 3 optimal things, and then like in other cases it may kind of change. So like learning this kind of model has been a bit challenging when it comes to like continuous environments, and I feel like this is typically the case when you're moving some, I guess, reinforcement learning algorithm from a discrete setting towards continuous settings, because I'd like to think that the real world is made of continuous quantities and stuff like that, and there should be some care taken as to how or what kind of model you're going to choose to represent that. Like for example, going from standard reinforcement learning to deep reinforcement learning, we need to care about how we represent our policy. So I'm going to use maybe some deep neural network, and this is going to, I guess, parameterize my policy. I also need to represent my action prior distribution. It's just there's so many things that you need to kind of like tweak and work with for you to have a fully working system.
Maybe as a way to start to wrap up, can you give me a list of kind of the top 3 things that you've learned about about deep reinforcement learning in general as applied to robotics, but with a particular emphasis on taking existing research results from the discrete domain into continuous environments?
Firstly, just moving from discrete environments to from discrete environments to continuous environments. I think one challenge with doing that is just representing, I think, your policy, right? So, for example, I think the first paper that I came across that kind of did like a good job with that was DDPG. It made me very interested in trying to apply reinforcement learning towards it basically like allowed me to believe that, okay, reinforcement learning will work in the robotics domain, right?
What's the name of that paper again?
I think it's deep deterministic policy gradients.
Okay.
Right. There's like a newer version, I think D4PG. I'm not sure, but yeah. But essentially, it's like an actor-critic method, and like it has all these. Okay, let me just say, like it's one of the first papers that kind of worked in deep in robotics, right? So to apply deep reinforcement learning in like with continuous environments, right? I think besides trying to learn like a good policy, you need to kind of think of exploration, like how you're going to handle exploring this very like your state space, given the fact that it's continuous and there's like infinitely many states that you can occupy there. And the other thing is data in robotics is very like it's very hard to come by. Like you kind of need to, or rather the ideal case is to not have a lot of is to not have to train your model for a long time, right? You'd like to maybe train your model like for a very short period of time, but like in reality, if you're using like these model-free methods, you find yourself training for a very, very long time, and that makes it difficult to kind of apply existing work, in the sense that maybe you have like you're working on your laptop and you can't run these models because it's going to take a long time to converge. And the other thing in reinforcement learning is that I realized it very late in my master's project, where like I realized the fact that your random seed is quite it's a very important thing, like, so you can blame the model all you want, like you get like a very good kind of learning curve, and you feel like, okay, this thing is working, you run it again. And what happens now, it basically gives you like a very flat thing and shows you that it doesn't work, so it fluctuates a lot. There's like all these variants. So I learned that, okay, for people to be able to trust your results, you need to be able to kind of average them over multiple runs. And multiple runs means that you're going to be running your algorithm for like a long time. And that is just more compute time. So like you need like, I guess, compute. Compute is a very important thing, So I'm fortunate enough to have access to a cluster. Like we have, I think, something with 60 blades like at the university, and I can basically run multiple experiments in parallel, and I can get my results within 2 hours or so, But the one challenge is just, you firstly looking for environments, you're looking for things that won't take too long, and then also, exploration has been like a very big thing. So yeah, I don't know if that answers your question, but those were, like, in my experience, things that I found very difficult about trying to apply deep reinforcement learning in the robotics domain. Just data and having very accurate simulations. Like, for example, you start out very, very ambitious. For example, we have a physical robot in-house here, like this mobile manipulator, and I'm like, I want to apply deep reinforcement learning, maybe learn to pick up a cup, and maybe the cup will have water and stuff like that. And as you kind of traverse through the literature, you start checking things off from this checklist, or like from these ambitions. It's like, okay, maybe there shouldn't be water, like in the cup, and then maybe the cup should be like a ball, something that's, I don't know, easier to hold. And then you're like, okay, maybe instead of having a ball, I'll be moving the manipulator just along like this, And then you keep going, and then you find yourself, okay, maybe instead of having a physical robot, I'm going to build a simulated version. And then when you're there, you're like, okay, instead of building a physical simulated version of the robot, I'm just going to build a simple 2D thing just to see if like these models work. And then you go all the way down to like a simple navigation domain, like a 2D thing where you can kind of easily prototype ideas. And so it's a very humbling experience. Like, you start out very big, and then like you kind of you kind of get to narrow down into these like particular problems, and you need something that's going to allow you to evaluate your ideas like quickly and very very efficiently and things like that. So yeah, like that has been my experience, I think, with deep RL in robotics, and I think other applications that I've been trying to use it in.
Yeah, and I think your experience is very much in line with the experiences of others, and has that kind of experience, I think, has led a lot of people to kind of leave deep RL in frustration and move on to simpler things. But it's it's certainly a space that I find fascinating, and thank you for kind of walking us through the way you're approaching it.
Yeah, thank you. Like, I really relate to like that last part. I understand people's frustration, and I understand the reasons if they end up leaving deep RL. Like, I think what has helped me stay here is the communities that I've been exposed to. Like, for example, I've met other people at the Deep Learning in Daba who are using deep RL for their unique applications, and we get to kind of talk. And if you're having a problem, you can ask this particular person. Same thing is happening at Black in AI, and like in some cases, I guess through Black in AI, you get to meet the leading researchers in the field, or the people who wrote the paper that's giving you sleepless nights and headaches, and you get to ask them directly, like, yo, what is this X like? How did you make this work? And what motivated your decisions, like, for, I guess, choosing this particular thing? So yeah, I really understand I guess the frustration and why people would be frustrated with the field. But hopefully going forward with this whole movement of trying to get people to release their code more, like this whole thing of reproducibility, problems like that will tend to die out. Yeah.
Awesome. Well, Sicelukwanda, thank you so much for taking the time to chat with me.
Thank you, Sam, and thank you for having me.
All right, everyone, that's our show for today. For more information on Sicelukwanda or any of the topics covered in this episode, visit twimlai.com/talk/235. For more information on the Black in AI series, visit twimlai.com/blackinai19. As always, thanks so much for listening, and catch you next time.